Hello all. Today I will be discussing my contribution to RnD Showcase 2021 on quantum bomb detection using the Zeno effect. Our work is based on one of the two most peculiar features of quantum mechanics called the quantum Zeno effect and the interaction-free measurements. The first one is basically an effect that allows you to slow down the time evolution of a quantum system by making repeated measurements on it often fast enough. While the other one is basically allows you to um, measure a property of an object without any interaction between it and the measuring device. These two effects have been used in one of the most dramatic illustration of quantum bomb detection experiment, which is basically a thought experiment designed by Elitzur and Weidman. The idea is very simple. What we will be trying to do is we will be having some bombs which can explode, and these are mixtures of bombs which can explode and bombs which are dead. So we will be trying to find whether the live bombs using the interaction-free measurement, and then we will be trying to use quantum Zeno effect to increase the probability of such live bomb detections. So experimentally, what we try to do is we try to do such a experiment using the Mach-Zehnder interferometers. But since we lack a quantum experiment or quantum optics lab, what we will try to do is we will be trying to simulate a quantum circuit, which is the analogous of the optics experiment. This quantum circuit has been shown to you in the right hand side, which is the first figure. So the trick to telling if a bomb is live or dead is fairly simple if you look at the quantum circuit. So without setting the bomb off, so what we will try to do is we will try to run a single qubit through the bomb again and again while making slow rotation, the qubit from 0 to 1 state. So this rotation gate for n times that will be trying to do that. It will be trying to change the state of the qubit from 0 to 1. So if the bomb is dead, the rotations will add up together until the qubit has rotated all the way to 1. And we stop after the appropriate number of measurements. So we will have basically a cutoff limit for these many measurements we have to do. And if we get an on result, so basically we know that the bomb was dead, it cannot explode. But if the bomb is alive, so what will happen is then after each rotation, there's a chance bomb will explode. Now we are rotating by some angle theta, which is in radian. So this rotation, this rotation is what I am talking about. So the chance of it exploding is equal to cos squared theta. But the bomb exploding or not is a measurement of the qubit. So it finally depends upon this measurement that we are trying to do. So when the bomb doesn't explode, our measurement will collapse it back to the off state. Now this is where the Zeno effect comes from. This means the rotation don't add up as they do in the dirt case. It will keep on going back to 0 again and again. So as long as the bomb doesn't explode, we keep ending up back to the 0 state. So we can add up all those, and if we get a 0 state, we kind of know that the bomb was actually it was a live bomb and it didn't explode. So we will get an off state after exploding, and we conclude the bomb is live. Yeah. How likely is the bomb will survive all the passes? Well, that's a tricky question to ask. So if we are saying we are rotating a state by n in every rotation, the ry thing. So my pn would basically be equal to cos pi by n raised to the power n. Now, if you notice that in a range in a limit to infinity, that this value will be close, it will be equivalent to 0. So that's where the Zeno effect comes from. That the constant measurements will in the longer run will overpower the sufficiently tiny rotations. So thus, by increasing the number of n's, the probability becomes arbitrarily close to 1, that after these many measurements, I am very much confident that my live bomb didn't explode and I can measure it using my interaction free measurements. So yeah, so this is somewhat counterintuitive, but we have tried to show you some results also. So if you can look at the results, where we have calculated the probability of qubit evolution and probability of live bomb being there, which is this probability has been tuned by this x raised to the power 1 by b gate. So if you can see, when the probability of qubit evolution is closer to 1 when the probability of live bombs is basically 0, so all of the bombs are dead. And as we are increasing a number of measurements and we are increasing the probability of live bombs, it's slowly the results is going to 0. But this is the what we say is the decoherence free assimilation. So what happens in the real term quantum systems is which is near term, so they have some noisy effects. So we tried to incorporate those noisy effects and had tried to do a simulation which had these decoherence effects too. Here we see after as we increase the number of measurement, we see a flat surface. That's because when we are saying we are increasing the measurements, what we are trying to say is we are increasing the number of times the experiment, the number of the depth of the circuit basically. So this block will be repeated n times if we are saying we are measuring n times. So because the decoherence effect will basically try to affect more to the system after a sufficient depth, it will basically collapse all of the quantum state to 0. So basically beyond I say 40 measurements, as results came out to be basically it was in the 0 state only. So that's how we can explain the results in this graph. So yeah, and that's what we try to do at our lab. We try to use quantum computing to solve various problems related to machine learning, natural sciences. And if you want to talk more, you can contact me on my email and you can find me here. Thank you.